So we are discussing the naive bias based on conditional probability of A given B has already occurred is equal to probability of A intersection B divided by probability of B, or probability of B given A is equal to probability of A intersection B divided by probability of A. The extended formula is probability of B given A multiplied by probability of A divided by probability of, this we call it as posterior probability, this prior probability. So posterior probability of event after evidence is seen. Bayes' rule in machine learning is an independent variable, and y it is a dependent. Probability of y given x has already occurred is equal to probability of x given y multiplied by probability of y divided by probability of x of y, probability of x occurring independent and multiple levels in dependent probability y is equal to k given x1, x2, x3 till xn is equal to probability of x1 given y is equal to k multiplied by probability of x2 given y is equal to k multiplied by of x3 given y is equal to k multiplied by probability y is equal to k probability of x1 into probability of x2 into probability of the naive Bayes rule for machine learning. Xn, we have Xn, you can go to Xn. So open the Excel sheet on which you are working in the last class. In sheet one, example one, we have worked on, right? Any doubts in example one? Okay, go to example two. So in the earlier class, we were looking at binaries, whether the car will be stolen, yes or no. Here we have three categories. It's a multinomial problem. Here, the dependent variable, three categorizations are there. So it's a multinomial dependent variable. So here, find the probability, the fruit type is and yellow. Three independent variables are long, sweet, and yellow. Find the probability, the fruit type is banana, if it is long, sweet, and yellow. So to answer this question, we need to calculate three probabilities. We have to calculate three probabilities. One, the probability that the fruit is banana, it is long. We also have to calculate probability of orange, given it is long, and we also have to calculate the third probability of fruit being other. Now, whichever has the highest probability, that will be the final probability. So let us calculate the first probability. So the first probability is probability of x1 is equal to long, given it is banana. Probability of x2 is equal to, given it is banana. Probability of x3 is equal to, given the fruit is banana. How many bananas are long? 400. Total number of bananas is how much? Is equal to 400 divided by 0.8. So 400 out of 500 bananas are long. So how many bananas are sweet? Is equal to 350 divided by how many bananas are there? 0.7. How many bananas are yellow? 450. Total number of bananas is 500. 400 divided by 500. This is 350 divided by 500. This is 450 divided by. Then comes your next part. Probability of likelihood of evidence. This is multiplication of all the three. Multiplication of all three, you will get probability of likelihood of evidence. Now we need prior probability of y is equal to banana. Probability of y is equal to banana. How many bananas are there? 500. Total number of fruits? 500 bananas, 1000 fruits. 500 plus 300 plus 200, na? So 0.5. So it is equal to 0.505 into 0.252. Copy the table down. Replace banana with orange. Now, how many of them are long and orange? Now, if any of this probability calculation is zero, the whole calculation will become. So, to avoid that, we have something called Laplace correction. Laplace correction replacing probability value closer to 0.01. So, a smaller value must be given instead of. So one of the problem with this bias probabilities is sometimes you will see the probability becoming Now, whenever the probability is becoming zero, the whole calculation will become, to avoid that, we use Laplace correction. So in this case, instead of zero, I'll take a value as 0.05, some random value. So the Laplace correction is implemented when one of the probability becomes, how many oranges are sweet? 150. How many total oranges are there? 300. 150 divided by 300. So 150 oranges are sweet. You can see in the table, 150 oranges are sweet. Total number of oranges are 300. So 0.5 is the probability. How many oranges are yellow? 300. 300 divided by 300. We get 1. Likelihood of evidence is multiplication of all the three. 0.05 into 0.5. Prior probability of orange is 300 divided by 0.075. Now calculate the probability of others. So how many other fruits are wrong? How many others are there? How many other fruits are sweet? How many of them are yellow? This is equal to 0.5 multiplied with 0.75, 0.25. 200 divided by 1000, 0.1875. So the highest probability is that if the fruit is long, sweet and yellow, we can say that. So this is a very important algorithm made by email spam classification. You know, Google classifies email as spam or not spam email. One of the first algorithms used was, now we are using neural networks and advanced algorithms, but initially email spam classification, which was implemented in Gmail, was based on Bayes algorithm. So it's a conditional probability based algorithm which creates probability tables in the backend and uses those probability tables for what we call predicting the values. For predicting, it uses the prior probability calculations, or whatever probabilities it calculated, it uses them for, stores them in the memory and uses it for prediction. वही ना last month में किया था ना installation. दो AC का installation किया था last month में February में. मैं घर पे नहीं हूँ, घर पे मेरे पेरेंट्स है, आप जा सकते हो डायरेक्ट. आप वो गूगल मैप्स में साई मोहन एनक्लेव बोल के टाइप कीजिए, वो एड्रेस दे देगा. साई मोहन एनक्लेव, ये रामनगर की तरफ विद्यानगर है. हाँ, अभी जा सकते हो. हाँ, वही शुभम रोड एक्सिस बैंक में सीधा आके अडिकमेट की तरफ रोड में है ये. वो शिवम रोड से आप इस तरफ आओगे ना, उस्मान यूनिवर्सिटी की तरफ, फिर वो नलकुंटा आरटीसी क्रॉस रोड जाने वाला रोड रहता है ना, वहां से 5 मिनट 10 मिनट का रास्ता है. साई मोहन इनके गूगल मैप्स में टाइप कीजिए, वो आ जाएगा. हाँ, ENCLAV. So Taiwan default data set will work on this, right? So go to UCI machine learning repository. We have 30,000 observations. UCI machine learning. Go to this website, UCI machine learning, or I'll send the link. So Taiwan credit default data set. I have sent you the link. Okay, download the data folder. You download, unzip the folder. Yeah. I have thorough change, model build check. You can add EDA and hypothesis test later. Credit data is equal to pd.read underscore Excel. File name is pip install Excel already. So credit data dot info. So we have 30,000 observations with all showing as ints only, right? Credit data dot columns. Now let us separate the columns. Num calls is equal to credit data double square bracket. Age is numeric. Bill amounts are numeric, right? And pay amounts are all numeric. So bill amounts and payments are all numeric. These are our numeric calls. Then object calls or cat calls, category calls is equal to credit data double square bracket sex, education, marriage, comma, pay 02. These are categorical calls. So total how many are there? 25, right? Dependent variable is also there, no? Okay, default payment next month. That we will take it as separate. So one ID column will delete. ID column will delete 24. Dependent variable 1, 23 independent variables. So we have separated the independent variables. Import CBON as SNS. Why is CBON taking so much time? Did you check correlation for numeric calls? Any multicollinearity is there? I don't see much of a multicollinearity. In heat map, we can see it clearly, right? So we have separated the data into numeric calls and, right, for pre-processing, right? There are no missing values in this data. So typically what we have done is, before splitting the data, you should have done EDA for num calls. You should do descriptive statistics. For cat calls, you have to do frequency value counts, right? Before we split the data, we should have normally done this. Num calls, descriptive statistics, cat calls, value counts, and histogram and density curve for limit balance. For limit balance, you should have done the numeric visualization. Hypothesis test also you could have done. What hypothesis test you have done? The average limit underscore balance payment next month, right? Default payment, because default has only two levels, right? Yes or no. Then you could also have done the average age default payment next month equal. Then you could also do ANOVA. ANOVA, what you will do? Underscore val of education equal. You could have also done test null, the average underscore val. What is the other variable we have? Is categorical equal, right? Then you also have to do chi-square test, which is very important here because the dependent variable is what? Categorical in binary, no association, marital status and default payment next month, no association, education and default payment. These are the tests, you do it later, right? And also do some visualization, some bar charts, stacked bar charts you can do. So you can do after here only some data visualization, hypothesis test, right? We will go to model building. Then we'll split the data. Now, what we have to do, dummy encode the cat calls underscore dummy is equal to pd dot get underscore dummies. Columns is equal to give the names of the columns, copy them from single square bracket to single square bracket, Control C, and paste them here, Control V. Cat calls dummy dot to check how many columns we got. 77 columns it created. Dummy columns 77 it created. 77 dummy columns it created. Anybody did the seaborne heat map? No, right? Multiple you are doing a multiple net is there. White square is there? Any white squares? Tell like a white squares on a map. Okay, no problem. Credit data underscore df is equal to pd dot concat. Make it x only. X is equal to pd dot concat num calls, comma cat calls dummy, comma axis is equal to 1. Row wise concatenation. Sorry, column wise concatenation. First num calls, then cat calls dummy. So we have separated the num calls and cat calls. All of you have separated them. And then we have dummy encoded the cat calls. We have dummy encoded the cat calls. You got it? Num calls and cat calls, we separated them. Dummy encoded the cat calls. Then we concatenated them into X, our independent variables. Credit data, square bracket, single quote, because there is a space in the name, right? There is a space in the name. Use square brackets, single or double quotes. Value underscore counts. So 23,000 people have paid it on time. 6,636 people have defaulted on credit card payment. 22,000 paid them on time. 6,000 have not paid on. 23,364 paid on time. 6,636 did not pay it on. All right, can we move forward? Now we have our data in X and Y. We have got our data in independent variables X, dependent variable Y. In all independent variables as X, dependent variable as Y. Now we are ready to build models. sklearn dot linear underscore model. What regression? Regression. The dependent variable is binary, 0 and 1 is equal to logistic model is equal to logit X comma Y. Oh, iterations have reached the limit. Max underscore iter. Oh, we should have done scaling also, right? Numbers in larger values. Okay. Logit model dot X comma Y. 77.87 is the accuracy. 77.87 is accuracy. Is equal to logit model dot predict from sklearn dot metrics confusion matrix display comma ROC curve. So once we have split the data into X and Y, we build the model and we got an accuracy of 77.87. Confusion matrix display dot from predictions Y comma, we have a problem actually. See, 1 and 1 it is predicting 0. Confusion matrix first is what? From predictions Y true, Y pred, right? First is Y prediction is logic predict. ROC curve display dot from Y comma logic predict. AOC is 50%, very bad prediction, right? The prediction is not good at all. So all of you build the model, logistic regression. All of you split the data to X and Y. X is independent variables, Y is dependent variable. Regression model, logistic regression model. Now people have done this, go to decision tree classifier. People have built, who built logistic regression, built decision tree, because the performance of logistic regression is very, very bad. AUC is 0.50, accuracy is 77. It is not predicting once, 0 predictions for one. Cross validation also you have to do for decision tree, no? Cross validation, cross underscore val underscore score. See, decision tree will overfit. Did you adjust the max depth? Cross validation you check, no, for decision tree, cross underscore val underscore score. From sklearn.model underscore selection, import cross underscore val underscore score, repeated testing. No. After decision tree only you have to do cross validation to check how much overfitting it is doing. So I am scrolling down. AUC also, you can see ROC curve 0.50 something will get ROC curve. sklearn dot tree decision tree classifier. Tree is equal to decision tree classifier. Tree model is equal to x comma y. Tree model dot score x comma y. 99.93. So it is overfitting from sklearn dot model selection val underscore score cross val underscore score tree comma x comma y. So decision tree classifier. The train accuracy is 99. Oh, test accuracy is around 72. So 20% difference is there. So what we have to do? Cross validation of max depth 10. Cross validation is also around 80%. Your train accuracy is also 84%. So this is the best fit model. The model is good. It's not overfitting. So max depth of 10 trees. Decision tree classifier with depth of 10 trees. If you do direct, it is giving overfitting. But when you fix the depth to 10, it is giving us a good fit model. How much AUC got? AUC for this decision tree. Area under the curve. Marginally missed the target, 0.69. So ROC curve is 0.69. See, the model seems good, but look at the AUC, 0.69. It should be above 0.70. So AUC marginally we are missing. We are marginally missing AUC. So let us look at random forest. Learn dot ensemble random forest classifier. RF is equal to random forest classifier. N underscore estimate is how many here? Model is equal to RF dot fit x comma y. sklearn dot ensemble import random forest classifier. RF is equal to random forest classifier. N underscore estimate is 1000. RF model is equal to RF dot fit x comma. నేను ఆఫీస్ లో ఉన్నానమ్మా, నేను వచ్చేటప్పటికి 7:30 అవుతుంది. గచ్చిబౌలిలో ఉన్నాను నేను, విద్యానగర్. వచ్చేటప్పటికి 7:30 అవుతుంది, 7:30 అవుతుంది. సో RF predict is equal to RF model dot predict. Meanwhile, sklearn. So we have different name bases for classification. Multinomial, when your dependent variable has more than 2. Categorical NB. So we have to use Gaussian NB. We have to use Gaussian name base. AUC of 1. AUC of 1. So it is not overfitting also. If it is overfits, AUC will be very less. But it will take a lot of time. If you want to run cross validation, it will take time. So let us not waste time. So let us run the name base. Okay. So this is the random forest. Once you have completed random forest, we will run it home or tomorrow we will run. Because it takes time, no? Okay. Going forward, sklearn Gaussian name base. NB is equal to Gaussian name base. NB model is equal to NB dot fit x comma NB model dot score x comma y. That is 644. Because we are thinking we better to use Bernoulli because a lot of them are 0 1s. 77 get them as we got. How drastically it improved Bernoulli. So we will use Bernoulli name base because our dummies are there. 77 columns are get dummies, 0 and 1. So Bernoulli is the Bernoulli means binary distribution, 0 and 1. Bernoulli's binomial distribution or Bernoulli is a statistician who discovered this binary distribution. Bernoulli's NB. So if we use Bernoulli's NB, we got 77.54. Gaussian NB was very bad because Gaussian NB works when most of your variables are numerical. Gaussian is normal distribution. No? The other name of normal distribution is Gaussian. So NB predict is equal to NB model dot predict of X. ROC curve display dot from predictions y comma NB predict. Oh, AUC is very less, 0.68 only. AUC is less, 0.68. So we will work on this data again later because we have problem called imbalance data. If you look at our dependent variable, 23,364 is 0 and only 6,600 is There's a huge difference, right, between yes and no. No is very high. Typically, we want no and yes to be closer to one another, not exactly equal. Like this, we want it. But we have data like this. No is very few, yes is very, very. This we call it as imbalance. This is what is causing the problem for the models to predict. So what we have to do, we have to two options. You bring the no's to equivalent to yes, or you bring yes equivalent to, we call it as balancing. Balancing, either by deleting data or by duplicating data. That we will discuss. Then we will have a stable model. Then we will have a stable performing model. The reason why models are not able to perform is because of the imbalance in no and yes. That you remember. We will do on imbalanced data complete. That time we'll do this again. We'll build the models on balanced data. Then you will understand why some models perform badly and some. So why we are putting Bernoulli? Because we have 77 binary variables. Dummy variables are all binary, right? 0, 1, 0, 1, 0, 1. And numeric variables, we have very few. So that's why I'm using Bernoulli's naive Bayes. And our accuracy also improved. Even confusion matrix will also be good. Right, comma, and B. So it is better compared to logistic regression, right? Logistic regression, this 0 was there. This prediction was 0. Whereas here, we got better prediction. Dot score will give you accuracy. True positive plus true negative divided by all put together. TP plus FP plus FN plus TN. Now, area under the curve, AUC or receiver's operating curve. Now, if you look at the x-axis, we have false positive rate. We have the true positive rate. Scores plotted on a graph, TPR and FPR. So they are two different metrics. They true positive in accurate dot score function, we calculate accuracy. We take all the four quadrants of, whereas in case of ROC, we are more bothered about the TPR and FPR. Now, what is this TPR and FPR? This table should clear all your doubts. So we use TPR and FPR to do AUC calculation. TP by TP plus FN, FP by FP plus TN. Accuracy is, this is the formula. No. We are, see, this metric considers all. True negative is not the numerator. No, it is false positive. Look at the false positive rate. This is TP plus TN, right? And bottom is, right. Here, TP by TP plus FN. Here it is FP by FP plus TN. This is completely different, false positive rate, ROC curve. We need to do this for ROC of true positive and false positive. So the dotted line is 50%, above 0.7 to 0.9. That would be better. This is the most preferred stable ROC curve. So typical ROC for a good performing model would be somewhere here, as much as possible closer to 0.96. So see, we are getting accuracy is not a problem here. In our case, this data and in most of the classification data, accuracy will not be the problem most of the times. Most of the problems lie in the AUC or ROC curve, where they drastically are. There are some other metrics we do. F1 score, recall and sensitivity are there. No? That also will be very bad. So we have to look at other metrics also. And looking at models, we can't go with one metric. In fact, in all statistics, we have to go with multiple metrics. It depends on the business problem. So like I told you, R square and RMSE, right? High R square, low. For classification, high AUC, F1 score is also there. 2 into precision into recall divided by precision plus. That is also there. Precision is nothing but false positive, true positive rate. Precision is again true positive rate. In classification, we have multiple methods. Primary is accuracy, then F1 score. All three of them should be stable and closer to one another. 0.7 to 0.85, something like that. So that you have to look at the things. So simply going with accuracy does not work in classification. You have to plot AUC, you have to print classification report also and find out whether the model is performing stably or not. In fact, there are many metrics. As we go into industry, you'll understand based on the industry. In SaaS, you get a lot of metrics. So as of now, we are dealing with basic metrics only. So once you join the companies and industry, based on the company sector or industry, some metrics are important, some are not important. Suppose in medical diagnostics, false negatives are very important, very bad. So in credit card default, false positives are very bad. In this data, false positive is very bad, right? False positive is what? The model is predicting that person will pay the bill, but actually he will not pay the, that is problem here, right? So it depends on the business problem also. So once you go to industry and once you work on some specific sectoral data, you will understand the logic behind the metric. So as of now, for regression, remember R square and RMS. High R square, low RMS. For classification, first accuracy 0.70 to 0.95, then AUC 0.70 to 0.95, and then F1 score. 0.70 to 0.9. Right. So for classification, we have 3 methods. Now, for imbalanced data, we also need to check precision, recall, and so tomorrow I'll tell you what that problem is, how it causes problem. Tomorrow we'll discuss. And tomorrow we'll also discuss support vector machines, SVM, the another next algorithm.